of comments about, I think, Matthias, you were going to make about the Blackwell table?
Yeah, a few things. So we got a lot of emails regarding this Blackwell table that was going to be downloaded just at the time when a few of the early birds requested it. It wasn't available yet, but now it should be up at courses.witson.com. You just go to the Blackwell table tab and download the Excel file, and we'll use that in the exercise at the end of this course. We're also getting a lot of questions regarding certificates, and we will not provide any certificates as a part of this course, and we're still trying to figure out some good ways of incorporating certificates in these free courses where we have so many different participants. So that might be available for the next course like this. We also get a lot of questions regarding whether the recording will be made available after the course. And yes, the recording will be made available after the course, and we'll send the recording or the link to the recording to everyone sometime later this week. So on that note, Curtis, you can just start where you left off.
Okay. Yeah. So with that, I guess I wanted to make some comments about, for those of you who might be familiar with a more compositional treatment of fluid behavior, and if not, then at least this will give you an introduction to that. But for practical purposes, just as an example, the reservoir simulator written by Keith Coates called Sensor is written basically with the same programming PVT logic and description for both black oil and equation of state. And the reason for that is because the gas oil ratio, which is what's kept track of in terms of the volume of stock tank barrels and the volume of standard cubic feet, that's kept track of in every grid cell from initially throughout the entire simulation run, is basically keeping track of 2 molar amounts of 2 components. And the overall GOR, wherever it might be, a given cell or wherever, is representing the total composition ZI in a compositional formulation. The little rs term is giving the molar composition of the surface gas and surface oil in the equilibrium gas phase, wherever it might be. Likewise, for any oil in any cell or wherever it might be, it's capital RS, solution gas oil ratio, is giving the composition of that oil. And every number in the Blackwell PVT table, correct me if I'm wrong saying, every number in the Blackwell PVT table that you'll find is labeled with a gas oil ratio. Okay? It's labeled with the gas oil ratio. And it's associated with a composition, and that composition has a specific saturation pressure. So it's got it's got a gas oil ratio and a saturation pressure tied to it. Now it also has a pressure tied to it, and that pressure may be greater than, or it might be equal to the saturation pressure. So in a way, you're basically keeping track in a Blackwell model of the total gas oil ratio in every cell, whether it's a single phase or 2-phase, and if 2-phase, then how many of the stock tank barrels are in the gas phase, how many are in the oil phase, and so forth. And you can do flash calculations, which in the case of compositional is basically how many moles of the total mixture becomes a gas phase of the total moles. That's the equivalent of basically the gas volume over total volume. Okay? And that's given by total gas oil ratio. You have to have the little rs and the big RS, the BO and the BG. With all of those numbers in a grid cell, you're able to find out how much of the grid cell is a gas saturation, how much is an oil saturation. Okay? And as we'll see later in my talk here and in the example, If you have the gas-oil ratio, you will immediately be able to assess what is the relevant saturation pressure for that system. Okay, so you can calculate, for example, from the Blackwell table, total volume versus pressure, shown here. Total volume versus pressure. You can calculate the total volume, the gas volume, the oil volume for a given gas-oil ratio and how that changes with pressure. So for example, if you're looking at an oil phase, it'll have an oil compressibility like this. It goes below the bubble point. Total volume goes up as gas evolves. Oil shrinks. The difference between total volume and oil volume is the gas volume. You can actually calculate that constant composition expansion curve from the Blackwell table. If it's a gas condensate, if it's a composition or has a little RS of 100 barrels per million, then you can go in, you'll know its dew point, and you'll know below the dew point, you'll know how much of the total volume is liquid and how much is gas. So you'll have the liquid dropout curve as well. In addition to that, you'll also be able to plot saturation pressure versus composition. Now the composition, there's only two components. We could take the mole percent of surface gas, and you'll get this so-called PX diagram. And the critical point, if your Blackwell table is what I call complete, that we'll talk about being complete, like the one you're going to work with in the example, then you'll actually have a critical point, a transition from the bubble point curve here, where you've got lower amount of the surface gas component. This is the bubble. Let me just draw it in here. This is our bubble point line along here. These are our bubble points. And I'll change color here to gas. And these are our dew points. I'm drawing now. These are our dew points, both upper and lower dew points. And here we've got our critical point. And it'll end up that for the Blackwell table, that critical point will always be the maximum saturation pressure. Okay? But all of this is intrinsically within the Blackwell table that you have. PX diagram, pressure volume diagram. I thought we'd do just a real simple how to convert from solution gas-oil ratio to molar composition. This is actually done, for example, in this reservoir simulator sensor. You actually get a table of what is the mole fraction corresponding to the RS. So let's just look at it. Basically, we've got the mole fraction. This is going to be the mole fraction of the component, surface gas component. I'm sorry, this is yeah. If you want to calculate convert the surface gas coming from the reservoir oil to moles, you have to divide by, in SI units, it's 23.68 standard cubic meters per kilogram mole. If you were doing it in field units, you'd use 379 standard cubic feet per pound mole. We're doing this in metric units. Okay, so we're converting this V surface gas from the oil over the surface oil, the volume. Okay. If we want to convert this to moles, we have to multiply by density to get mass, divided by molecular weight to get moles. So this will give us the ratio of how many moles became surface gas to how many moles became surface oil. Okay. Well, this term here is nothing more than the RS. Okay. Okay, and if I'm using Ecofisk, that's a big 6 billion barrel field in Norway. Approximately 300 standard cubic meters per standard cubic meter initial solution gas oil ratio. The stock tank oil density around 850 kilograms per cubic meter, and average molecular weight of stock tank oil about 200 kilograms per kilogram mole. So if we just calculate this, somebody's got a calculator here, hopefully. And we got basically this 300 number. And then we've got up on top, we're going to bring the molecular weight, 200 kilograms per kilogram mole. And down below, we've got the 23.68. And then we've got the density of 850. And I believe this is close to about 3.
Yeah, 2.98.
2.98. Okay? And that's kilogram mole per kilogram mole. Okay? So the mole fraction, that's gas, surface gas component, that's just NGO over NGO plus NOO. That's the total moles, right? Well, that's then equal to 2.98. That's what ended up in the gas, surface gas phase. And we've got 2.98 plus 1, which is from the ratio, what's in the oil phase. Oops. There we go. That, I believe, is around 75%. Three over 4. Okay, that means that the mole fraction of the surface oil product in this original Ecofisk oil is 25 mole percent. So it's a very straightforward, and because the black oil model has a constant surface oil density and a constant surface gas density, it'll always be 850 and always be 200 that you're going to be using to do the conversion. Okay, so you have the means by which you can convert gas oil ratio or oil gas ratio to mole fraction. In fact, they give the equations here in the next. Okay, these are the equations to make that conversion back and forth. It's a compositional model. It's just 2 components. These are for the SI units. Should give you the same numbers if you put in the equations. Now, one of my colleagues at the university recently made the comment that black oil tables should be banned from existence. They were just bullshit, and that we should do everything compositionally. And to keep my blood pressure down, I basically didn't reply. But the point is that the black oil model is a compositional model. The black oil model is a compositional model, and it does a phenomenal job of describing, as Singh will be showing here in his presentation, of complex reservoir simulation processes of very complex near critical oils, near critical gas condensates, retrograde condensates. What you see is that you're able to describe for sure 99% of all depletion processes for any kind of fluid type compositionally with a black oil model. It's been shown by Keith Coates, originally in 1982. We have a couple of papers on it ourselves. It is a compositional model. It's a simple 2-component model. But it's a special 2-component model. And I'm going to bring this question up because this was something that Keith asked me, I think is maybe 15 years ago. We're just sitting around. He was smoking a cigar and I was drinking a Coke. And he asked me the question, so why can't we just use the 2-component equation of state instead of these damn black oil tables that have all the problems of negative compressibilities and on and on and on and on and on? There are lots of challenges with black oil tables to get them really right and consistent. So why can't we just use a 2-component equation of state to get an equally good or maybe even better description than a black oil model? And we'll come back to that at the end of my talk and see what the answer is, yes or no. Next on the agenda, how do we create the black oil PVT models? Well, old school, like this is when I came to Norway in 1978, it was still old school. I was learning to program on my calculator all of the standing correlations and so forth and so on for black oil PVT properties, okay? And you could do that and can still do that for some reservoirs. Basically reservoirs that don't have many stock tank barrels dissolved in gas, in the gas phase. So it's okay for some oils up to about 1,000 cubic feet per barrel, but you have to have very lean gas condensate. So immediately the incipient gas coming out of that 1,000 cubic feet per barrel oil, that gas coming out of the bubble point at 3,500 psi is probably going to have 32 barrels per million in solution. So you can't ignore the little RS term. And there are no correlations for the little RS term of any accuracy. So you can use it for some low GR oil reservoirs, yes. And if you do so, then you can maybe tune the original correlations to the lab data that allow you to do this. But it's basically not done much anymore. Now it is used in things like Prosper, where they use black oil tables, black oil properties for doing pipe flow calculations more often than not. It's not used much to create black oil tables for reservoir simulation. I don't think we've seen the last 25 years a single black oil table come in created by black oil correlations. Now, instead we use the equation of state, and this basically, just to repeat what Matthias has told, you need an equation of state, you need a composition, or a bunch of compositions actually, separator process. You need some way to create these compositions of the depletion process, which Singh is going to tell us about. And then we sometimes, and we like to do it all the time, but we sometimes definitely need to extrapolate to saturation pressures beyond the initial saturation pressure of the original reservoir fluid, okay, for reasons I'll get into. This is what we published in 1981. This was basically the origin of how to create a black oil table from an equation of state model, or you could even do it from constant volume depletion data as shown in the paper. But basically what you did is that you had equilibrium gas, equilibrium oil. You took the equilibrium gas by itself. You basically separated these two. You took this gas, its composition, put it through a process, and you got these surface gas from reservoir gas and surface oil from reservoir oil. Different nomenclature back then. This is now we call this. And then you took the oil phase out here, put it through the same process to get the surface gas from the oil and the surface oil from the oil. Okay, now we've got the volume here, pressure and temperature. You got the volume here, pressure and temperature. And in that paper, we did it from the constant volume depletion type experiment, okay? And it only worked from the initial dew point pressure downwards. But this has been generalized basically to use for any type of experiment. And as you lowered the pressure in the PVT cell, you got a different vapor, a different liquid, and you did the process again, and you accumulated all these PVT properties. Basically, this was the introduction. Now, so let's just take this more generic version of this. So we've got our so we need this at many different pressures. Now remember, every black oil table we're creating is at a constant temperature, right? It's always going to be at a constant temperature. You can pick your temperature, you can redo the same experiment with the same initial fluid and so forth. But you basically need to create equilibrium vapor, equilibrium liquid phases at a wide range of pressures, okay? And the original method was that, what's the default is that we start with this black oil composition that we're going to start with is just equal to the initial reservoir composition of what's in situ in the reservoir, okay, times 0. it's only an oil or it's only a gas. If you got a gas and an oil, it's a little more complicated. But the point is that you start with this, and this has an associated saturation pressure, be it bubble point or dew point, which I'll write PSI, initial saturation pressure for that. And using one of the depletion type experiments that Singh's going to talk about, CCE, CVD, which was the original Whitson-Torp method, or DLE, we could basically create these equilibrium vapor and liquids by depleting, starting at the initial saturation pressure and going down to standard conditions or some low pressure. Okay? As many pressures as you'd like. So basically a monotonically decreasing pressure. But what if this initial saturation pressure was 100 bar? That means we don't know anything about saturated properties of oil or gas phase above 100 bar. So the generalized recommended best way, which none of the softwares have, except one we use called phase comp, is that what you want to do is that you want to collect compositions. I'll use the J nomenclature from the original paper for pressures all the way from some low, maybe not standard conditions, some minimum, all the way out to a critical pressure. In fact, we'll put in here SI, critical. And likewise, every time we have an equilibrium gas phase, okay, this is going to be a saturated gas, and it's saturated oil. It doesn't have to be the saturated oil, but normally it will be. From the same pressure, we're going to go and get a complete collection of saturated compositions, okay, so that we cover the entire range of, and don't stop here, but actually go all the way out to the critical point. So that's this recommendation. That's normally what we're doing. What we want to do is when we go all the way out to some critical point. And then you can basically run all of these compositions through the separators to come up with all of the properties to get the complete table. Okay? That allows you to get so in the lower pressure region here, we'll use some kind of a depletion test. And in this part out here, we have to use some kind of extrapolation. And there's a number of methods to do that type of extrapolation. And we can come back to that in questions if somebody wants to discuss that. Okay, so now we're going to talk about how do we use Blackwell PVT models. And this is something that I was certainly never taught per se. What normally happened is that we would look at Blackwell tables, figures, Blackwell figures. Everybody's looked at Blackwell figures, okay? You know, the saturated, the BO and the RS, the undersaturated, saturated, okay? But nobody uses graphical images to get numbers to make calculations of initial gas and oil in place. I can promise you that, okay? You don't get enough significant digits, and you know The president of the company wants to know how many new billions of barrels you just discovered. And so you go get your BO with 2 or 3 or 4 significant digits to use to get that number. So looking at figures is one thing, but how we actually use them in our software, be it reservoir simulation, MBAL, material balance, pressure transit, whatever it is you're trying to, when you need a BO, an RS, a MUO, there's a certain process that you have to go through of logic for the program to get that out of your table. Okay, and this is the procedure that's kind of not written anywhere that I've seen, including in the monograph that we wrote, not written in any of our papers. But this is the algorithm that Keith Coates and Ian Cheshire and all these people, Jim Nolan, who have written these reservoir simulators have to use, or anybody has a tool where you need black oil properties, be it saturated or undersaturated, from a table. This is the procedure you have to use. And it is exactly identical, analogous to how you do it compositionally. You start with the composition, and you want to know what's going on at a given pressure and temperature. Start with the composition. You've got a pressure and temperature. What do? Okay. And you have this in every grid cell in a reservoir simulator, in every element of a tubing model, or you're just simply treating the entire reservoir as a uniform composition. The first thing you have to do is find out how many phases exist. 1 or 2 phases. Is it only gas? Is it only oil? Or is it gas plus oil? It's the first thing you have to figure out. The next thing, once you know that, then you can go look around in the tables for the 3 black oil PVT properties, R, the B, and the viscosity for each phase. So you might have 6 total, or you might have 3 total. That's it. So now we're going to look at the recipe or the procedure, how that's done. Now this is very cryptic, what I'm showing you, but this is the logic that you have to program to get these numbers. So the first question, is it saturated or undersaturated state? That is for a given gas oil ratio, given pressure, temperature. So the first thing you do is that you go look into the saturated part of the table, and you find in the table, you look in the table at the highest saturation pressure you have, okay? You look at, which is PSI. That's the highest saturation pressure you have in your table. Might be a bubble point. It'll actually be a bubble point. And then you get, what is the maximum RS associated with that? What's the maximum? We're going to call this big RS, little RS, just the solution gas oil ratio at that pressure. Okay, the highest saturation pressure you have. Now, on the little RS, at 1, if you actually have the table down to 1 atmosphere, the little RS at 1 atmosphere may be larger than the initial little RS. Okay, so it's not the largest little RS you have in the table, but it's the one at the maximum saturation pressure. Once you've got these 2 maximum numbers, you then will take your gas oil ratio that you actually have, and you say, is it less than my maximum solution GOR? If it is, we've got an oil. Then you go in and you read for the gas oil ratio you have, you say, well, that's my solution gas oil ratio. What is the bubble point from the curve? And you assign that to saturation pressure. If you find that the gas oil ratio you have is larger than this inverse of the little RS max, then it's a gas. Okay? And then you read the dew point from that saturated curve. Now you look at the pressure. You've got this pressure here. You're going to compare it. So now what this gives us is the saturation pressure for our gas oil ratio. And now we go and ask, is it a saturated or undersaturated condition? So if it's saturated, you go basically and read the properties at the pressure. Okay? And if it's undersaturated, then you'll know if it's a gas or you'll know it's an oil, and you go fetch the 3 single-phase properties, be it gas or oil, depending on what the gas-oil ratio is. This is the logic that you use. Is there anything I've done wrong, Steve? No. Yeah, this is it. Okay. So this is an example figure that I had sent me yesterday. And it's just an example. What this figure does, and we use it all the time, this is the solution gas-oil ratio. So for the oil phase, this is RS, and for the gas phase, it's 1 over little rs. All on the same figure. Okay. Now, if we say that we just have a discovery here, and we've got our discovery on test, 1,000 standard cubic feet per stock tank barrel. Okay, that's 1 MSCF per stock tank barrel, which is the unit here. That's right here. So we go into this curve. This is doing what we did in that cryptic stuff on the previous page, that cryptic stuff. You basically just go in and you find this point right here. Okay, it's got a bubble point here of, okay, well, the first thing is this. The GOR is less, okay, this is the RS max. First we had RS max found first. That was equal to 2,000, about, I got good eyes, 2.2. I think I remember the number from the table. Okay, so it's less than this. That means that we're down here. Okay, the GOR we have, this is our GOR, 1,000. It's less than the 2,200, so it's somewhere down here. So we go in here, we read the bubble point here. That's 40, about 4,500 PSI. Okay. Now, from 4,500 PSI A and outwards at any pressure you like to use, you've got all of the undersaturated properties you need, BO and viscosity. If your initial pressure is right here, you just go into your table. This is the oil we've got. It's got this 1,000 cubic feet per barrel with a 4,500 bubble point, and at 8,000 pounds, you can go get properties BO and mu. If instead we've got a gas condensate, our test is 10,000 standard cubic feet per stock tank barrel. Okay, that's little r SI of 100 stock tank barrels per million standard cubic feet. Okay, that's right here. We go into there. First, we know that 10,000 is larger than little rs max. Little rs max there is about 1 over 5,000. I can read it off the curve. This is a GOR of about 5,000 on a log scale. Okay, so that's 200 stock tank barrels per million. Because our 100 is less than 200, then we know it's a gas. Okay, and we need to go get its dew point, and that dew point is right there. That dew point is, looks like about 5,200. Okay, now if the reservoir pressure here was, 10,000 pounds, then we would go all the way out here with the undersaturated properties until we reach the 10,000 pounds. It's right in here. Okay, and we would get our mu G and our BGD. That's graphically doing what that previous slide is telling you to do. Okay, so you first find the RS max values, and then you check what your actual GOR is relative to that. If it's less than that, then you know it's saturated. You have to find out the saturation pressure, and you get all the properties. So this is, we're going to do an exercise with this. Okay, but this figure nobody draws. Okay, you've got two figures actually. This figure here is usually done like this. right? And this figure here looks like this. Okay. So you can do it on the two figures separately, but we like to put them together for a reason we're going to come to now. So this is the procedure that you use to identify whether it's saturated or undersaturated and what properties you can and need to fetch, and you do it in this manner. We're going to do an example of that. So now we're to the final kind of like, call it topic. And basically this is some special challenges of Blackwell PVT problem. Incomplete saturated Blackwell PVT table. Okay? There's a range of GURs that do not have an assigned or known saturation pressure. That we see right here. Between this GUR and that GUR, we know nothing about the saturated or undersaturated properties. Nothing. And you're going to let some Yahoo, Ian Cheshire, or somebody wrote the PVT package for Eclipse 100 do the extrapolation for you into that black hole, and ain't going to do it. No, it will do it for you, right? See? But yeah, it'll do it, but we don't know how it does it. Okay. We don't want to go there. Okay. So we're going to look at this. The second two problems, negative compressibilities, which everybody has experienced who's done Blackwell simulation, can come about for, I think, 3 reasons. These were the 3 reasons I thought of. Sing's the expert, so we'll see whether I get an A or a B. Insufficient number of saturated pressure notes, particularly if it's near critical, where everything is highly nonlinear. Well, I'm not going to draw it, but basically, if you don't have enough, I'll just draw it here. If your curve looks like this on the RS, and you've got your points like this, you're going to get negative compressibilities. You need lots and lots of points to get these derivatives right. Okay? 1, insufficient saturated phase properties. I'm sorry, inconsistent saturated phase properties. What that would mean is that you've got initial gas cap and initial oil. You create your saturated gas properties by depleting the gas cap composition to get all the gas properties, and you deplete the oil composition separately to get all the oil properties. The only time they're truly in equilibrium is at the initial GOC conditions. After that, they're not really equilibrium. That will also potentially give you negative compressibilities. The third one is that the Blackwell PVT is not created from the US model, but instead they got they bottom a French curve, or they just correlations, and you don't know how they got the numbers. So there's a number of reasons you can get negative compressibilities. And the last challenge is that if the Blackwell PVT approximation is just inadequate, first you have to prove that. Okay? So you have to actually prove that it's not adequate. So that's a challenge. That's the challenge there. Well, these last two items here, negative compressibilities and whether it's adequate or not, I'll send you to a couple of papers. Now there's one paper on is the Blackwell approximation adequate or not? The first paper discussing that is Keith Coates, 1982, which that paper will also make available, where he specifically shows 4 gas condensates. Blackwell model can be used for every depletion situation and for even gas cycling in some cases. So there's some papers there. We're not going to talk about those. I just want to talk briefly about this incomplete saturated Blackwell PVT table. Okay. This is the typical producing gas oil ratio of any reservoir, be it an oil reservoir or gas condensate reservoir. It starts at a number and goes up. If you look at oil reservoirs, it starts at the initial solution gas oil ratio, maybe stays constant for a while, and then it climbs up to some maximum. Then maybe it turns around. By then, you're ready to sell a field. So this is basically the behavior that you always expect. Now, what's interesting is that if you create the Blackwell table from this initial oil composition, you won't have any saturated properties, maybe the entire curve here. Okay? You don't have any saturated properties for these producing gas oil ratios. What's happening there? In this interval here, gas oil ratio, the gas oil ratio is going to start. You've got them for these, but you don't have any properties from 2200 to 5000. Okay. So what if we need, or would we ever need, saturated, undersaturated properties for these gas oil ratios? Okay. Maybe 10% of the time, maybe 15% of the time, but not 0% of the time. And I'll explain. Using the conventional method where you start at the saturation pressure here, you're going to be missing a lot of saturated problems, and it can cause problems. So this is the example I was showing. In this pressure, in this GOR range here, we don't have any saturated or undersaturated properties. Question is, why might we need them? Okay, why might we need them? These are just two examples. If you've got commingled production where multiple zones and at least one zone's got a gas condensate, another zone's got an oil, okay? So for depletion, each zone's got the Blackwell table, no problem, okay? Because you're always, you hit the bubble point or the dew point and you go to lower pressures. But what happens if they're commingled when you shut the well in? Start getting oil moving into the gas zone or gas moving into the oil zone, and it goes to high pressures when you shut it in. So very easily you could get in this situation where you're at pressure greater than or equal to the saturation pressure, and where you're in this you're at a GOR greater than the RSI, and you're at a GOR let's say be less than 1 over little RSI. Okay, this is this problem area. Okay, and we have no properties. That situation is not so uncommon. Commingled production. Why? Because it takes fewer wells to develop the field, is less money. Second reason is if you're modeling single well models of gas condensate wells, if you're trying to study condensate blockage and compositional effects before and after shut-ins, looking at well test CGR variations, whatever it might be, what you'll find is that near the wellbore, maybe as far out as 100 meters, that you're going to get during the shut-in what was originally a gas condensate gas phase will turn possibly into an oil phase or a two phase at exactly in the same region here. So this is another situation where you can get where you have the need to have the saturated and undersaturated properties for this interval here that we don't normally have properties for. So these are just two examples. So how do you do that? And there's one of the papers I mentioned is there. But basically what you want to do, this is our 1 over little rs. This is our RS curve. What you want to do, this is the maximum, PSI. What you want to do here is that you want to extrapolate that curve here somewhere or another and extrapolate the RS curve up here where they meet together. Okay? How to do this? That's another webinar. Or you go read the paper that that's referenced earlier. There's a number of ways to do this, some with the equation of state, some without the equation of state, and there's a lot of challenges and issues, but it can be done, and sometimes it must be done. So the point is that it basically you need to close this gap by extrapolating the gases and the oils in a consistent way.
So we got a very good question from Mark here regarding these. I guess his question is: those producing GOR ratios are not representative of equilibrium mixes, are they? Question mark. Typically, the higher GORs are because disproportionate free gas volumes are producing with oil.
Yeah.
Question mark.
Yeah. So they're not representative of. Well, how should I put it? They're real. They happen. You get them for these two reasons here and other reasons. So you do actually get them. If you do a compositional simulation, you get them. Okay? And you need to know the saturation pressure of all the mixtures between the original, let's say, zone with oil and the other zone with gas. So if the two zones start mixing, you create lots of real mixtures. So they do become real. The question is how to create them in a physically consistent manner. So in that case of a zone A and zone B, gas and oil, you might do the extrapolation by just mixing that gas from zone A and the oil from zone B until you reach the critical. So you cover that range of all the different types of mixtures. So that would be one way to go about doing it. So there's not a unique, completely correct way to do it. But there are ways to do it. And the only way to check and see is that a good enough way is to compare it with an equation of state compositional simulation to see if there's any significant differences between the two caused by that. Okay. So that is I think that was everything I wanted. And I wanted to come back to this question. Did we come to this question before the break?
Yeah.
I think I was gone during the first hour. I felt like I was in another world.
We did. Yeah.
Okay, so the question is, can a two-component EUS model, because the equation of state won't have this problem. None of these problems, right? See?
Yeah.
You don't get any of these problems that I wrote up here if you're using the equation of state. We can't take a hand raise, I guess.
Hard.
Okay. So what I'm gonna try to explain, and it's not trivial to understand it, but the answer is no. And Keith was not happy. Because the beauty of using two components, it's faster than black oil, it's more stable than black oil, more robust. You don't have to think about all these. It was so great that it was a disappointment. I didn't get dinner. Okay, for 2 days. The answer was no, because the problem with using a two-component equation of state is that the properties of the two components are constant for all mixtures, all compositions, and everything. Now, what really happens is that when you create black oil tables from a multi-component equation of state, which is what you normally do, you get all this fidelity and resolution in the component distributions changing in the gas phases and the oil phases, and as a function of pressure. It's capturing all of that. The 6 saturated PVT property, black oil PVT properties, when they're created by an equation of state, they describe the oil and gas phases correctly, where they have differing surface oil C7, C5 plus, C4 minus, surface oil, surface gas. The component distributions of these vary for each phase and as a function of pressure when you're creating the black oil tables. So all of that variation is captured in the VO, RS, BG and little rs. You'll never capture it with a two component equation of state because those two component properties are truly constant. You need at least 4 components. A light gas and a light oil, a light gas and a heavy gas, and a light oil and a heavy oil. You need at least 4 components to get the kind of description that you actually get from a black oil model.
Good. And just a couple of questions here. If you flip back a slide or 2 there, we stop there.
There.
Follow-up question from Mark on the last cartoon there, Curtis. One cartoon back. From Mark again about these GORs, that there will be no grid block with those GORs in situ. Will they only manifest in tubing? Question mark.
Okay, so if you don't turn the simulator on, the answer is yes. In situ, that's time 0. You're not running the simulator. As soon as you turn the simulator on and it starts running, you can get all sorts of reasons, only these 2 of which I give it. So yeah, so you have yeah, no, it can definitely happen in reservoir grid cells. Yeah, for sure.
Good. Another from Jefferson Creek in Gulf of Mexico deep water. The I guess the saturation pressure is less than 2,000 pounds, and you can have initial reservoir pressures of more than 18,000 pounds. Properties must be extrapolated over a long range and are not real. How does one address this?
Yeah, so hi Jeff. So let's just take an example: 2,000 pound bubble point, 12,000 pound initial pressure, and what I would do is I would not use Eclipse 100, because Eclipse 100 I think is the only simulator that requires these properties to be saturated properties, I think, to be extrapolated out.
Yeah, if you don't give them, it will extrapolate.
Yeah.
But it will not use the extrapolated. In this case, it will not use it.
If it's only single phase oil, for example.
Yeah, if you have the near undersaturated.
Then you just need to go with
undersaturated GOC, then it's you need to have.
Yeah.
But in this particular case, even if you don't extrapolate, do the simulation depletion, there will be no problem.
No problem. Yeah. So it's yeah. So
there can be negative compressibility issue, because the negative for checking the negative compressibility,
yeah,
what it does, it will extrapolate the saturated properties from 2,000
to 12,000. Yeah.
12,000, and all pressure points, it will check for the negative compressibility.
Yeah.
And then there will be issue of negative compressibility, but not issue of any.
But it won't affect anything.
No.
As long as you don't start seeing these anomalous high GORs localized, you know.
Yeah, if there is commingle.
Yeah,
whatever.
yeah, commingle might or something, or gas injection. Or, yeah. So if you. So I think what Singh's saying is that you can get a lot of warnings, but you shouldn't get into a problem if it's just depletion of that kind of reservoir.
Good.
I think bottom line, the way to check is using a composition model or just a simple sector model or something, and just doing comparisons to see whether the performances are similar or the same.
Yep.
Which is what you're going to show us now.
Yeah, so
it's yeah. Any other kind of questions that several people have? Or?
No, so now it's good. So I think we can take a 4-minute break, and then we can set up Singh on that computer, and then Carson get some coffee, and then we'll.
So let's.